Hi, I'm Mohammadreza Behrouzi. We are proud of ourselves that you watch our videos and we can make a small contribution towards your knowledge improvements. These videos that we have uploaded on our website or on our YouTube channel consist of notes and real case examples from our last projects. Those projects were performed by a team of professionals and experts. Therefore, by watching these videos, you can gain tremendous amount of knowledge and experience by which you can design your process units, your plants with highest safety. You are our only sponsor. So if you enjoyed the video, at the end hit the like and subscribe so that you can get informed about our latest videos. In these episodes, I'm going to present you with the information about the most important chemicals in my perspective, which is added to cooling water systems, corrosion inhibitors. So at first, it's going to be explained why we need corrosion inhibitors in cooling water systems. Then I'm going to talk about different categories of corrosion inhibitors. Afterwards, I'm going to elaborate upon the formulation of corrosion inhibitors and the components which are incorporated in that formulations. Lastly, I'm going to review a real case study about the corrosion inhibitors. So I'm going to start here why we need corrosion inhibitors to be added to cooling water systems. As a brief review, corrosion reactions of metals in water are electrochemicals in nature. They consist of two separate reactions: an anodic reaction in which metal is dissolved to produce metal ions in solution and corrosion products either on the metal surface or dispersed in the water, and a cathodic reaction in which dissolved oxygen is reduced to form hydroxide ions, or in acid solution hydrogen ions are reduced to hydrogen gas. Thus, when a steel corrodes in water, the anodic reactions are in this way, and the corresponding cathodic reaction is the reduction of oxygens in this manner, or in acid solution, the reduction of hydrogen ions happens in this manner. These reactions involve a transfer of electrons. This means that an electric current, called the corrosion current, must flow from anodes to cathodes through the metal surface and back to the anode through ions in the water. So here, because of the corrosions resulting from anodic reaction and cathodic reactions, we need to inject or add corrosion inhibitors in order to prevent these processes, these reactions from happening. But in order to make you better understand how it works, to give you an overall overview of its mechanism, of course, we're going to talk about its mechanism and how it works excessively in the middle of the episodes. But right now, to give you some understanding, this is the picture, a good picture from Nalco Handbook. Here we have the base metal. Here we have added corrosion inhibitors to create the film on the base metal. An effective anodic film is impermeable to both ferrous iron and aggressive ions in solution like chloride. If there are breaks in the film like these ones, ferrous ions can be transported into the solutions, and chloride can penetrate the film, increasing the corrosion rate. So here we add corrosion inhibitors to create the film. Therefore, it is protected against any kind of malign ions such as chloride. As some aggressive ions, it is protected against aggressive ions like chloride here. But sometimes these chloride ions becomes excess, and of course they find their way to break the field and impact the base metal. Therefore, ferrous ion can be transported into the solution, and it can, in fact, as a result, corrode the base metal. Another picture I want to show you is this picture. An effective cathodic film is impermeable to oxygen and effective insulator for electron transfer. Breaks in the film allow oxygen penetration and reduction with electrons in the metal, increasing the corrosion rate. So when we add corrosion inhibitors, uh, the oxygen can't find the way. But unfortunately, sometimes because of some situations, because of maybe the loss in the film thickness, the oxygen finds its way and of course grab the electron in base metal and becomes these ions, and as a result base metals becomes corroded. So we must monitor the feed of corrosion inhibitor to cooling water systems on a daily basis and check the results on daily basis. Polarizations: any process that interferes with either the anodic or the cathodic reaction, or with both reactions, will reduce or stop the flow of current and hence reduce or stop corrosions. Two naturally occurring processes that limit the flow of corrosion currents are called polarizations and passivations. Most corrosion reactions in water systems are self-limiting. The products of anodic and cathodic reactions, ferrous and ferric hydroxides at the anodes and hydroxides and calcium carbonate at the cathodes, tend to shield the metal surface and prevent ready access of water containing dissolved oxygen. This process, called polarization, limits the rate of cathodic reaction and hence reduces the corrosion rate. For this reason, initial high corrosion rates tend to slow down and approach a limiting value that depends upon the configuration of the surface and the composition of the water. High flow velocity and high turbulence can overcome the polarization effect. Corrosion rate then increases because corrosion products cannot accumulate to help shield the metal surface. Then we have passivation. Elements that are high in galvanic series are so reactive that they cannot exist as the free elements under atmospheric conditions. Sodium and potassium, for example, react violently with water. These are in effect simply extremely rapid corrosion reactions. However, other elements such as magnesium, aluminum, and zinc that are also very reactive as free elements are stable in contact with air and water and are widely used as materials of constructions. The difference is that these elements form stable oxides film that effectively seal the surface and prevent all contact with water and air. This process is called passivation. The dull gray film seen on the galvanized steel that has been exposed to air is a good example of naturally formed passive film. Stainless steel earned the title by forming a very thin, mostly invisible film of chromic oxide on the surface that prevents corrosion. An important property of a naturally formed passive film is that they are self-repairing. If the film is damaged, a small amount of corrosion occurs to reform the film and the surface again becomes passive. This is true as long as the environment doesn't attack the oxide film. Thus, galvanized steel is commonly used for cooling water construction. However, the pH of water must not be allowed to range below about 6.5 or above about 8.5. Outside of this range, the oxide film dissolves and the zinc coating corrodes away. Similarly, stainless steels are stable in sulfuric acid, which provides an oxidizing atmosphere, but they corrode readily in hydrochloric acid, a reducing acid. So to summarize what we have learned from passivations and polarization, uh, some elements such as magnesium, aluminum, and zinc are free elements and of course are stable in contact with air and water. And of course they form stable oxides films and can effectively seal the surface and prevent all contact with air and water. This process is called passivation. About polarizations, the products of anodic and cathodic reactions such as ferrous and ferric hydroxides tend to shield the metal surface and prevent ready access of water containing dissolved oxygen. This process called polarization. So we have polarizations and we have passivation. Passivation is self-repairing while polarization is self-limiting. Now let's move to the corrosion inhibitors categories and types. Corrosion inhibitors are simple inorganic or organic chemicals that when added to water at ppm dosage levels interfere with electrochemical corrosion reactions on a steel, copper or other material and dramatically reduce corrosion rates. Specific corrosion inhibitors are discussed in the following sections. Corrosion inhibitors as a group fall into three general classifications: reactive inhibitors, precipitating inhibitors, and filming inhibitors. Reactive inhibitors chemically react with the metal surface to produce a protective film that is chemically bonded to the surface and contains both oxidized metal and some form of the inhibitor. These films are quite stable, they are resistant to velocity and turbulence effects, and usually provide some residual corrosion protection for time if inhibitor feed is discontinued for any reasons. Chromate and nitrite on steel and various azoles on copper are typical examples of reactive corrosion inhibitors. Precipitating inhibitors provide corrosion protection by precipitating an inert barrier layer on the metal surface. These layers are not chemically bonded to the surface, but when well formed, they can be quite resistant to flow, velocity, and turbulence. Zinc forming zinc hydroxide films and phosphate forming ferric and calcium phosphates are typical examples of precipitating inhibitors. Then we have filming inhibitors. Filming inhibitors are chemicals such as amines, organic acids, and other polar organic molecules that form chemical or electrostatic bonds with the metal surface without actually corroding the surface. Many of these molecules contain a charged ionic group at one end that attaches to the surface and and a hydrophobic group that extends outwards and helps to keep water away from the surface. Filming inhibitors are very useful, but they are the least stable to flow velocity and turbulence. Filming amines used in boiler condensate corrosion control are examples of filming inhibitors. So, to summarize what we have learned from different types of inhibitors, and of course, to compare them, their characteristics, reactive inhibitors chemically react with the metal surface and chemically bonded to the surface, while in precipitating inhibitors provide protection by precipitating an inert barrier layer on the metal surface. These are not chemically bonded like above, but when well formed they can be quite resistant to flow velocity and turbulence. Typical examples of reactive inhibitors are chromite and nitrite on steel and various others on copper. Zinc and phosphate are typical examples of precipitating inhibitors. For filming inhibitors, they function based on their structure of their molecules. Their molecules has two ends, and in one end we have a hydrophobic group, and in other end we have hydrophilic groups. Hydrophobic group extends outwards and help to keep the water away from the surface. Then corrosion inhibitors are also classified in terms of corrosion reaction that they inhibit. Cathodic inhibitors interfere with the cathodic reaction, reduction of oxygen. Reduction of oxygen. Corrosion reactions in cooling water environments are under cathodic control. That is, the rate of the cathodic reaction governed by the rate at which dissolved oxygen can diffuse to the metal surface controls the overall corrosion rate. By reducing the available cathodic area, cathodic inhibitors proportionally reduce the overall corrosion rate. So, this paragraph states an important sentence here. It says that the main corrosion in cooling water piping stems from cathodic reactions. So if we try to reduce the cathodic sites by adding corrosion inhibitors, we can dramatically control, we can dramatically reduce and control cathodic corrosion, and as a result, overall corrosion. Anodic inhibitors. We have cathodic inhibitors because, as you know, we had two reactions, and of course, cathodic reactions and anodic reactions. Anodic inhibitors suppresses the anodic reaction, that is, metal ions going into the solutions. Anodic inhibitors are very effective in controlling general corrosion because they directly protect the corroding sites. However, anodic inhibitors can also stimulate pitting attack if maintained below a critical concentration. Since the overall corrosion reaction is under cathodic control, reducing the available anodic area does not directly reduce the corrosion rate. It simply concentrates the attack on any available anodic sites. As explained more fully in this chapter, this can lead to serious localized pitting corrosions. For this reason, anodic inhibitors are also called dangerous inhibitors. Minimum concentration of anodic inhibitors required for good protection have been determined experimentally for each product. This concentration will vary somewhat with water quality. High dissolved solids and low alkalinity waters will require high inhibitor dosage for safe protection. So, here says that, of course, it is correct that the overall corrosion is controlled by cathodic reactions, and of course, if we add cathodic inhibitors, we can protect the systems. But it doesn't mean that we should not add anodic inhibitors, because if we do not add anodic inhibitors, it means that we can create an environment in which localized corrosion such as pitting might happen. Therefore, uh, anodic inhibitors, which help to prevent this kind of occurrences, prevent this kind of processes, should be added to the system on a minimum basis. They have some minimum required and minimum basis, required and minimum concentration for these anodic inhibitors, which should be formulated, which should be added to cooling waters in order to protect the system from localized attack or from pitting. Then we have mixed inhibitors. Mixed inhibitors are blended products that suppress both anodic and cathodic reactions. This is a desirable way to gain benefits of the good protection of anodic inhibitors with added safety from the overall reduction in corrosion rate from cathodic inhibitors. Many commercial corrosion inhibitors are formulated in this way. Then we have general inhibitors or filming inhibitors as above cover the entire surface of the corroding metal through the development of absorbed protective films. Sometimes these films are polymeric in nature. Inhibitor selection. Many different corrosion inhibitors alone and in various combinations are available to provide protection to the engineering alloys used in cooling water treatment. However, selecting the proper inhibitor is not always a simple matter. A good understanding of the system, including water chemistry, operating routine, system metallurgy, and critical heat exchanger, is required along with good product line knowledge. So these parameters are good parameters in order to select the best type of inhibitors. They should be checked, they should be evaluated in order to be able to select the best type of inhibitors. But among these inhibitors that we discussed here, reactive inhibitors, they are categorized into they are categorized into two groups, from reactive inhibitors, precipitating inhibitors, filling inhibitors, and another group was, cathodic from another perspective, cathodic inhibitors, anodic inhibitors, and mixed inhibitors and general inhibitors. From the first perspective, precipitating inhibitors are widely used in cooling water system in oil and gas industry. So, for from first perspective, precipitating inhibitors are most commonly used in oil and gas industry. From the second perspective, uh, mixed inhibitors are used because they are, a combination of both anodic and cathodic inhibitors, and they can protect all metal surfaces, all types of metals. Here, I'm going to talk about the different component required for the formulation of corrosion inhibitors. As I just stated, corrosion inhibitors are a combination of anodic inhibitors and cathodic inhibitors. Therefore, different components are incorporated in the formulation of one specific corrosion inhibitors. I'm going to show you a table before going and talking about before going to talking about the each of these component excessively. I'm going to show you this table in order to give you uh, overall perspective toward these matters. As I stated, we have anodic inhibitors, cathodic inhibitors, and some inhibitors which act in both directions, act as anodic and cathodic inhibitors. These components, nitrite, orthophosphate, bicarbonate, silicate, and molybdate, are principally anodic. Carbonate, polyphosphate, and zinc are principally cathodic, and azoles, phosphonates, organic filming amines are both anodic and cathodic. We should select at least one of these elements from each of these table. One from this column, one from this column, one from this column. At least one component. It sometimes it could be two components depending on the perspective and experience of that manufacturer of the corrosion inhibitors. So we have nitrate, orthophosphates, bicarbonate, silicate, molybdate, carbonate, polyphosphates, zinc, azoles, phosphonate, organic film amines. And here I'm going to talk about right now. I'm going to elaborate on some of the most important, inhibitors. I'm going to start with uh, chromate. Chromate is included in this manual because of its historical significance. Before about 985, chromate was used extensively as a corrosion inhibitor. It is a reactive anodic inhibitor, extremely effective over a wide range of operating conditions, especially in open cooling tower systems when blended with cathodic inhibitors such as zinc or polyphosphates. However, in the late 98 in the late 80s, chromate was banned because of its toxicological impact on the environment. Chromate is a known carcinogenic. With uh, chromate no longer available for open system use, other inhibitors had to be developed to provide needed corrosion protection. Newer products are more environmentally friendly and can be equally effective. So chromate, because of its impacts on the environment and on the human beings and on the human health, is banned from in the late 80s, and they are no longer produced and no longer used as the corrosion inhibitors in cooling water systems. Then we have zinc. Zinc is a mediocre corrosion inhibitor for carbon steel when used alone. However, it is a valuable synergistic addition to almost all other corrosion inhibitors in open cooling water systems, providing an added level of cathodic precipitation type protection to reduce the overall corrosion rate. The precipitated film is zinc hydroxide or a complex zinc hydroxycarbonate, depending upon the circulating water composition and temperature. These films form preferentially at cathodic sites because of local high pH conditions. Some of the benefits of adding zinc to any corrosion inhibitor formulation are improved protection, more tenacious film, faster film formulation, lower required concentration of other inhibitors compared to use without zinc. So zinc is a mediocre corrosion inhibitor, but when it is added to the corrosion inhibitors formulations and it is used with other corrosion inhibitors, it can help to improve protection. It can create more tenacious film. It can cause faster film formation, and of course, it can contribute to lower required concentration of other inhibitors Of course, we're going to talk about other inhibitors, and of course, in the information about the other inhibitors, you're going to see that it is stated that if they are used with zinc, lower required concentration of them are required. Zinc, therefore, is always used in formulation with other corrosion inhibitors. The effective maximum pH for zinc-containing system without stabilization is 7.5. Above pH 7.5, zinc hydroxide precipitates in the bulk water so that corrosion protection is lost. However, this problem is easily solved by incorporating zinc-stabilizing polymers in the formulation. These polymers help to prevent zinc hydroxide from precipitating in the bulk water, but allow it to form under higher pH conditions that exist at cathodic sites. With polymers present, zinc-containing corrosion inhibitors can be used up to about pH 8.5. Effective zinc levels are between 0.5 and 5.0 ppm as zinc. Proper selection and dosage of the stabilizing polymer is critical for the success of this program. Zinc is rarely used in closed systems. So here it states the overall, to summarize this, it states that zincs, we have to use some polymers in order to stabilize the zinc. If we want to use the zinc containing corrosion inhibitors above pH of 7.5. So if I have a cooling water system whose pH is about 8.2, I'm supposed to add polymers to my corrosion inhibitors in order to stabilize the zinc complexes, because zinc hydroxides precipitates in the bulk water above pH 7.5. So I should be extremely meticulous in the formulation of corrosion inhibitors. And of course, if I want the zinc to be effective in its performance, I have to add this amount, minimum this amount, and maximum this amount. So with the passage of time, we are creating the formula for our corrosion inhibitors. We know that it has, for instance, some elements A, B, C, D. The A element is zinc. The B element is some types of polymers. And right now we have to, and of course, as I stated here, zinc is a principally cathodic. So at least I have checked this, I have ticked this principally cathodic, I have selected at least one component from these ones. So as I stated, it has many components. Component A is zinc, component B is polymers. So component B are some types of polymers in order to stabilize the zinc components. Now let's go to discuss other components and see what we have. Orthophosphate. Phosphate-based chemicals are the most widely used corrosion inhibitors in open cooling water system. 3-sodium orthophosphates with this formulation is simply the 3-sodium salt of orthophosphoric acids. The disodium and the monosodium salts are also available. These are widely used for pH and alkalinity control in boiler water treatment as well as in open cooling water system. The orthophosphate anion is the simplest species in this family of corrosion inhibitors. It is an anodic precipitating inhibitor that effectively inhibits the corrosion of low carbon acyl by precipitating ferric phosphate at anodic sites. Good corrosion control can be achieved above pH 7.5, especially in soft water systems. Before this pH, orthophosphate is less effective because ferric phosphates become soluble. Phosphate chemistry is sensitive to water quality, especially chloride content. High concentration of chloride above 300 ppm reduce the efficiency of orthophosphate-based corrosion inhibitors by promoting localized pitting attack. When orthophosphates can be used, protective film formation is very rapid and tenacious. Orthophosphates works synergistically with other inhibitors to provide excellent corrosion protection, similar to chromite. A major concern with orthophosphate is the potential for calcium phosphate precipitation in high pH and hard waters. It is often suggested that orthophosphates should also act as a cathodic corrosion inhibitor because 3-calcium phosphates becomes very insoluble at higher pH levels generated at cathodic sites. In fact, this is probably correct. However, 3-calcium phosphate precipitates slowly as the end product of a chain of complex intermediate phosphates, while ferric phosphates precipitate quickly at the anodic sites. Therefore, in a corroded system, any corrodic inhibition achieved by orthophosphate is overshadowed by the intermediate anodic protection provided by ferric phosphates. In a well-protected system where little or no corrosion takes place, 3-calcium phosphate, if it is allowed to form, will provide additional cathodic corrosion protection over time. So let's review again what we have learned from this passage about orthophosphates. First, our most widely used corrosion inhibitors. So I've seen in almost every formulation of corrosion inhibitors from different manufacturers, they incorporate orthophosphates as one of the components of their formulations for corrosion inhibitors. So they are widely used corrosion inhibitors. Trisodium and the monosodium and disodium are different types of orthophosphates, different sources of orthophosphate. They are categorized as anodic and precipitating inhibitors, and they are in fact categorized in this group orthophosphate here. As I stated, at least we are supposed to select one component from this one, and we select orthophosphate from this group. And of course, it effectively inhibits corrosion of low carbon steel by precipitating ferric phosphates. And of course, good corrosion control can be achieved above pH 7.5. High chloride content can reduce the efficiency of orthophosphate-based corrosion inhibitors. When we use orthophosphates, protective film formation is very rapid and tenacious. It's really important parameter. It works synergistically with other inhibitors, especially zinc, to provide excellent corrosion protection. And of course, the major concern here is that there is this potential for calcium phosphate precipitation in high pH and hard waters. Then we have polyphosphates. Phosphates. Chemistry is a complex subject that is behind the scope of this manual. Briefly, phosphates can polymerize, just like many organic molecules, to form several different classes of polyphosphate compounds. The compounds most often used in cooling water treatment includes the dimer, the trimer, the dimer like this, the trimer like this, and sodium hexametaphosphate. Polyphosphates are classified as cathodic precipitating inhibitors. They react with calcium under high pH condition to form a thin protective film of calcium polyphosphates. Polyphosphates provide corrosion protection for carbonaceal in an effective pH range from 6.5 to about 8. A minimum of about 50 ppm calcium hardness is essential if polyphosphates are to function as corrosion inhibitors. Other than hardness, polyphosphates are relatively insensitive to water quality. Sometimes polyphosphates are combined with zinc, another cathodic corrosion inhibitor, to improve performance, as I stated earlier. A concern with polyphosphates is that they revert to form orthophosphate and increase potential for calcium phosphate precipitation. Reversion rates are increased by low pH and high temperature. Pyrophosphate is the most stable of the common polyphosphates, while tripolyphosphate is the least stable. Conveniently, the potassium salt, tetrapotassium pyrophosphates, is very soluble so that liquid formulations containing pyrophosphate as a corrosion inhibitor can easily be made. Because of their ability to form soluble complex ions with calcium, polyphosphates are sometimes used as chemical softening agents in domestic water supplies. So, to summarize what we have learned about polyphosphates, we know that polyphosphates are cathodic precipitating inhibitors. Remember, zinc is also cathodic precipitating inhibitors. And when we have zinc in our formulation, in most situations there is no need to have another cathodic precipitating inhibitors. So there is no need to incorporate polyphosphate in our formulation because we have zinc as a principally cathodic inhibitor in our formulation. Anyway, they react with calcium under high pH condition at cathodic sites to form a thin protective film of calcium polyphosphates. So in order to be effective for polyphosphates, they need some required amount of calcium to in fact create a protective film of calcium polyphosphates. And of course, this minimum amount is 50 ppm of calcium. So in cooling water systems, when we use polyphosphates as our corrosion inhibitors, we need to have a continuous and minimum amount of 50 ppm of calcium in our water in order to help polyphosphates to create, in fact, calcium polyphosphates protective film on cathodic sites. And of course it provides good protections in the pH range from 6.5 to about 8, and these are the different types of polyphosphates as you can see here. Then when polyphosphates are combined with zinc, they can improve their performance. And unfortunately, a concern with polyphosphate is that they revert and to form orthophosphate and increase the potential for calcium phosphate precipitation. And this reversion rate is a function of pH and temperature. Pyrophosphate is the most stable type, while 3-polyphosphate is the least stable one. And because of their ability to form soluble complexes ion with calcium, polyphosphates are sometimes used as chemical softening agents in domestic water supplies. Then we have phosphonates. Organic phosphate compounds are called phosphonates. Remember, phosphonates are distinguished from inorganic polyphosphonates in that, remember, polyphosphonates are inorganic while phosphonates or organic phosphates. So phosphonates are distinguished from inorganic polyphosphates in that all phosphonates contain direct carbon-phosphorus bonds. Phosphonates are primarily used in cooling water treatment to control calcium carbonate scale, but they also have corrosion inhibiting properties. Phosphonates belong to the class of compounds known as general precipitating inhibitors that protect both anodic and cathodic sites. The compounds that precipitate to form protective film are calcium and iron salts. The composition of the film depends upon the phosphonates, the specific blended formulation in use, and the composition of the circulating water and operating condition. Before going further to talk about different characteristics and problems associated with phosphonates, I want to show you here we have selected zinc from this group, principally cathodic. We have selected orthophosphate from this group, and here we have selected phosphonate, which acts as both cathodic and anodic inhibitors. So three components of these ones are selected. Hi, I'm Mohammadreza Behrouzi, the manager of Educational Institute for Equipment and Process Design. I hope that you have enjoyed every moment of this video. I highly recommend you watching videos instructing separators from our websites or through our YouTube channels. By watching these videos, you become not only familiar but also professional in design of various types of separators for different applications. So far, if you have enjoyed the video, hit the like and subscribe. A problem with all phosphonates is that, like polyphosphonates, they decompose over time to form orthophosphates. As a group, phosphonates are more stable than inorganic polyphosphonates, but decomposition rates increase with temperature and with low pH. Phosphonates are also attacked by oxidizing biocides such as chlorine and bromine compounds. All of these factors must be considered when designing chemical treatment programs, including phosphonates. This sentence is extremely important. I have, I've been in these situations. I have experiences all of these situations with high chloride, without chloride in normal situations, in normal conditions, and different formulations have been used for that, for those scenarios, for those situations. Here, the polyphosphonates has four common types. HEDP, when used alone, it is a relative poor corrosion inhibitor. However, when formulated with zinc, it provides good protection. The effective pH range is 7 to 9. HEDP requires at least 25 to 50 ppm calcium as carbonate in the water for film formulations. However, at calcium levels above about 300 ppm as calcium carbonate, HEDP can precipitate as a calcium HEDP salt. This can lead to loss of both mineral scale and corrosion control, and to formation of calcium HEDP scale. Polymers can be added to the formulation to help prevent precipitation of calcium phosphonate salt. HEDP is more resistant to attack by coloring than is AMP, but not as resistant as PBTC. Then we have AMP, also is a relative poor corrosion inhibitor when used alone. In the presence of zinc, excellent corrosion protection on carbonaceal can be achieved, especially in soft water. AMP contains a nitrogen atom to which three methylene phosphonate groups are bonded. These nitrogen bonds weaken resistance to chlorine, so the AMP is rapidly degraded. The effective pH range is 7 to 9. AMP is more tolerant of high calcium level than is HEDP, but in high hardness water, AMP can form a complex and precipitate a calcium AMP salt that can add to system skin. Then we have PBTC, is one of the most stable of the phosphonates. It will not degrade in the presence of typical chlorine level in cooling water systems. When used with zinc, PBTC can provide excellent carbon and steel corrosion protection. It also has good tolerance towards calcium, so that calcium phosphonates precipitation is not a potential problem. Then we have HPA, is a phosphonate that was specifically designed for carbon steel corrosion protection rather than calcium carbonate scale control. When used alone, HPA requires calcium in the water for effective protection of carbon steel. However, in combination with zinc, HPA provides excellent corrosion control on carbon steel in soft water. HPA degrades easily with low level of chlorine in water, but the manufacturer claims that this reaction can be controlled by adding monoethanolamine to the formulations. So here we have four types of uh, phosphonates: HEDP, AMP, PBTC, and HPA. In terms of comparison, in terms of coloring resistance to coloring, uh, if I want to compare them, PBTC is the most powerful one, the most resistant one. HPA is the least resistant one. And so in first place, PBTC gets the first place, HPA, HEDP gets the second place, AMP gets the third place, and HPA gets the last place. HEDP, when all of them, when the HDP, PBTC, AMP, and HPA, all of them, when they are used with zinc, when they are formulated with zinc, they can provide excellent corrosion activity against corrosion mechanism. HDP requires 25 to 50 ppm of calcium in order to form the layer. And of course, sometimes if the calcium is present in abundant amount, it might cause some creation of some calcium HDP salt, which might cause some which might impact the corrosion performance mechanism, corrosion performance of this, corrosion control performance of this HEDP. The same happens to AMP. But AMP is more resistant to high amount of calcium, but at the end it's gonna impact its corrosion control power. This is not a problem. The amount of calcium in water system is not a problem for PBTC, and it's not going to impact the PBTC performance against corrosion mechanism, against corrosion reactions. And of course, HPA, like PBTC, requires calcium in order to create that protection of carbon steels. And as I said, it is the most degradable one against the high level of chlorine. So far we have talked about of different components which could be used, which could be incorporated in the formulation of uh, corrosion inhibitors. In order to create a kind of formulations for general corrosion inhibitors, I've created this kind of a sketch for myself, and of course whenever I want to teach to some of flow process engineers these instructions about corrosion inhibitors, I use this sketch for in order to make them better understand the different components of formulation for corrosion inhibitors. As I stated, it has some parts, some components. It consists of some components A, B, C, D, E. I showed you in the text that it was written that always we use zinc because it has many advantages. It is extremely beneficial to use zinc as one of the components because it can reduce the constant, it can reduce the required amount of other corrosion inhibitors in the systems. When we use zinc, less amount of other corrosion inhibitors in the formula are required. It can help, in fact, other corrosion inhibitors to show excellent performance against corrosion reactions, and it can help the protective film to be more tenacious. As I stated uh, when I was explaining about the zinc zinc performance. Then we use a polymer because we need to stabilize zinc complexes when the pH goes above 7.5. As I stated, sometimes some complexes above pH of 7.5, some complexes of zinc are created which might precipitate in the water and in fact impact the corrosion performance, corrosion control performance of zinc or other inhibitors. Therefore, it is common practice to use some types of polymers in order to stabilize those complexes when pH goes above 7.5. And of course, zinc is a principally cathodic inhibitors, and we need a principally anodic inhibitors. We talked about orthophosphates, and as I said, in the formulation of corrosion inhibitors, it is correct that it is a fact that corrosion reactions are controlled by cathodic reactions, by cathodic mechanisms, but it doesn't mean that we should not use principally anodic inhibitors because, as I stated, and it was really important, as I stated, when uh, when we do not use anodic inhibitors, some problems such as localized attack might happen on the surface of carbonaceous, which is known as pitting corrosions. And of course, in order to prevent this kind of occurrences, this kind of mechanism from happening, this kind of processes from happening, a minimum amount of anodic inhibitors is added to the formulations in order to prevent this kind of processes. So here, this box belongs to orthophosphates. Then we said that we need a general inhibitors, a mixed inhibitors. A general inhibitor is a mix of anodic and cathodic inhibitors. It doesn't mean that it has two of them. No, phosphonates acts as both cathodic and anodic inhibitors. As I stated, we have different types of phosphonates. We have HEDP, we had AMP, we had PBTC, and of course, we have HPA. And as I stated, these types of phosphonates are some are impacted by the level of chlorine in the water. They are not resistant to high level of chlorine in cooling water. And uh, we categorize them against this level of chlorine in water, and we said that PBTC is the most powerful phosphonate in terms of resistance to a high level of chlorine. uh, when we have a cooling water in which there are abundant excess amount of chlorine, we use PBTC as the phosphonates. But when we have a cooling water whose condition in which we don't have a lot of chlorine, the level of chlorine is not that high. We can It is a common practice to use HTTP instead of PBTC. Some manufacturers make this kind of formulations. They use HTTP instead of PBTC when there is few amount, when the chlorine level is not that much to impact in fact the HTTP. Therefore, they use HTTP in their formulations. But sometimes I've seen some manufacturers use a combination of HTTP and PBTC as phosphonates. So when for these components, for this part, when the chlorine is high, the level of chlorine in cooling water is high, we use PBTC. When the level of chlorine in water is not that much, we use HTTP or a combination of these ones. And of course, we have another element which is water, which is the main component, and it is crystal clear to us. But before ending our episodes about corrosion inhibitors, as I promised, I want to review a case study about the cooling water system of the petrochemical company I work for. I prepared these documents in order to, during the starts of companies, the process engineering department is supposed to perform a field trial, a test run, whatever you want to call it. In that field trials, different manufacturers of specific chemicals are invited to participate in that program. And of course, their chemicals will be tested. Each of these chemicals of each manufacturers will be tested for about 1 or 2 or 3 months. And process engineers are supposed to fill in some log sheet, fill in some information about the consumption of those chemicals, about the activity of those chemical, performance of those chemicals in the log sheet, and after the contest, after the field trial, each of the performance and consumption of each of those products will be compared and evaluated, and the best chemical of a specific manufacturer will be selected and will be used for 1 year. And of course, I prepared these documents to provide some information about the cooling water systems. And during that the preparation of these documents, I provided good informations. And I think it would be dramatically, it would be greatly useful if you review this document. The open-type cooling water system is applied for the MECO methanol project that include the counter-flow mechanical draft type cooling tower, cooling to water pumps, side filter, inhibitor, and dispersing dosing facility. The normal cooling water demand is this amount, and the max demand is this amount. Meteorological parameters for cooling tower design follows the air conditioning designs and meteorological data. Dry bulb temperature is 48 degrees Celsius. Wet bulb temperature is 33 degrees Celsius. And technical parameters for cooling water systems as follows. Of course, don't worry, you can download this PDF from my websites and read all of this information and compare it with your cooling water systems. Cooling water supply pressure is 4.5 bar gauge. Cooling water return pressure is 2.5 bar gauge. Cooling water supply temperature is in this range, and cooling water return temperature is in this range. Concentration cycle is 10 to 15. Makeup water normal consumption is 150 to 200 cubic meter per hour, and normal blowdown is 50 to 20 cubic meter per hour. And this is the normal sketch. This is the PNID diagram of cooling water systems. These are the facilities, dosing facilities, dosing tanks and dosing pumps here, including biodispersant, corrosion inhibitors, biocides, and oxidizing biocides. Here is the cooling tower. It has four cells, and here is the makeup water, which is RO. And as I stated, it is the consumption of RO, the makeup water, is about 200 cubic meter per hour. And here are the our side filter. Here it is cooling water side filters. About 5% of the water is passed through this side filter and returned to the basin. And this is the basin of cooling water systems. And these pumps are the supply pump to the end user, and the supply pressure is 4.5 bar gauge. And here is the return. It goes through from here it is supplied to the end users, and here is return from the end user to the cooling water. And here we have packing. It is showered from packing, and the air is goes up. And here we have induced fan, and the pressure of the return water is approximately 2.5 bar gauge with a temperature of 48 degrees Celsius maximum. Here is the overall view of our cooling systems, and here are the technical parameters. The heated circulating water returns in the cooling tower by residual pressure and go through the packing, then in the water pot after heat exchange with air. The cooling water is delivered to the user by cooling water supply pipe, as I explained. A screen is installed on the suction pit. The makeup water source of cooling water system is the preheated water. The blowdown is pumped to the outside of the plant. Two rows of side filters are applied for cooling water system, and each row consists of 8 sets of filters. Cooling tower, 4 cells, 3 run and 1 standby. The capacity of each cell is 4,500 cubic meter per hour. And this is the characteristics of RO makeup. Its pH is turbidity, TDS, chloride, and total iron are presented here, as you can see here. Here is this section is devoted to uh, corrosion and scale inhibitor. But before going to these sections, I want to show you the operating parameter range. These tests are performed on a daily basis in the laboratory of or petrochemical company. And of course, this is the ranges. These are the ranges of different tests. pH should be maintained between 7.2 to 8. Turbidity is less than 0, is less than 10. Cl this chloride is less than 60 ppm. COD in this range. TDS should be in this range. Total iron should be maximum 1 ppm. Of course, we keep it lower than 0.1 instead of a maximum 1 ppm. It is too much. And of course, other characteristics here you can see for yourselves. So the basic formulation that I in fact offer to the manufacturers was this ones. It the compositions consist of these parameters, these components: zinc chloride, PBTC, phosphoric acids, and polymer. Zinc should be minimally zinc should and of course I gave this percentage as minimum. Zinc should be about 4%, PBTC should be about 10%, and orthophosphates should be about 8%, and polymers should be about 20%. And remember that I have used PPTC as a phosphonate for these formulations because the zinc chloride is this amount and sometimes it might goes higher than this amount. Therefore, I wanted to stay on the safe side, so I selected PBTC instead of HEDP. And of course, I've given this notice. Note that due to chlorine additions, manufacturer is not allowed to incorporate HPA or AMP since they degrade in the presence of chlorine. So far we have talked about, let's have a review about what we have learned through these episodes. We have talked about corrosion mechanism. We said that we have two corrosion mechanism. Anodic corrosion mechanism consists of anodic reaction and cathodic reaction, and we said that cathodic reactions is the paramount, is the most important one, is the more important one, and of course it controls the corrosion reaction. Here are in fact anodic reaction and cathodic reaction. Then we talked about polarization and passivation, what polarization and passivation is, or and we said that when elements such as magnesium and aluminum and zinc are used, and of course they are stable in contact with air and water, they can seal the surface and prevent all contact with water and air. This process is called passivation. And for polarization, we said that the products of anodic and cathodic reactions such as ferrous and ferric hydroxides tend to shield the metal surface and prevent ready access of water containing dissolved oxygen. This process is called polarization, and we said that while polarization is self-limiting, passivation is self-repairing. Then we talked about corrosion inhibitors from different perspectives. From one perspective, we categorize into three uh, groups: reactive inhibitors, precipitating inhibitors, and filming inhibitors. Reactive inhibitors tend to bond chemically with the metal surface, while precipitating inhibitors tend to uh, not create a chemically not create a chemical bond with the surface, but when they are well formed, they can be quite resistant to flow velocity and turbulence. And of course, we have filming inhibitors. Their function are their function is based on their structures. They have their molecules have two ends, hydrophobic and hydrophilic, and based on these structures they function. In fact, a hydrophobic group that extends outward and helps to keep water away from the surface, the way they function. And I stated that in for cooling towers in oil and gas industry, precipitating inhibitors are used. And of course we discussed these corrosion inhibitors from from another perspective, from the reactions perspective. We divide them to four groups: catalytic inhibitors, anionic inhibitors, and mixed inhibitors and general inhibitors. Catalytic inhibitors are added in order to inhibit the in fact catalytic reactions. Anionic inhibitors are added to prevent anionic reactions. And here we stated that the minimum required minimum amount of anionic inhibitors should be used in order to prevent localized attack or pitting corrosions. And we have mixed inhibitors. Mixed inhibitors are combination of different types of inhibitors, and we said that we use mixed inhibitors because they can cover all corrosions for different types of metals, and therefore they are more complete, and they can show better performance against corrosion. And we use mixed inhibitors for oil and gas industry cooling tower systems. Then we talked about the formulation of corrosion inhibitors. We talked about chromate. We said that because of its impact on the environment and human health, they are banned. They are no longer used and produced. We talked about the most important, corrosion inhibitors, zinc, and of course, we said that it is principally catalytic inhibitors. And since it has this kind of advantages, improve protection, lower it helps to lower required concentration of other inhibitors. It helps to create more tenacious films, faster film formulations. We use zinc in all of the corrosion inhibitor formula. And of course, we said that since sometimes above pH 7.5, zinc hydroxide precipitates in the bulk water, and the corrosion protection is lost. We have to add some polymers in order to stabilize their performances and these complexes. And of course, we said that this amount of zinc should be added minimum in order to in order to show good performance against corrosion. Then we talked about uh, orthophosphates, and we said that they are anodic precipitating inhibitors. They are also used in almost corrosion inhibitor formula. And here we discussed some types of orthophosphate, and here we said that uh, a high amount of colorides contents can impact their efficiency. Then we talked about polyphosphates. We said that they are a type of phosphate. They are inorganic phosphates, and these are the different types of polyphosphate. What we said that, and of course, polyphosphates are principally catalytic precipitating inhibitors. And since we have zinc as the catalytic precipitating inhibitors, we do not use any more polyphosphates in our formulations. And of course, for polyphosphate, we said that they need 50 ppm of calcium in order to be able to create a protective film on the surface of the metal, like 50 ppm. And uh, sometimes polyphosphates are combined with zinc in order to, in some corrosion inhibitor formulas, in order to improve their performances. But in a typical, as I stated, in a typical corrosion inhibitor formula, we do not use zinc and polyphosphates together because they are from the same group. And we talked about a problem with the polyphosphate, that they revert to form orthophosphate and increase the potential for calcium phosphate precipitation, and it is a function of pH and temperatures. Then we talked about phosphonates. We said that they are principally anodic and cathodic inhibitors. They act in both directions, and we talked about different types of phosphonate: HEDP, PBTC, HPA, and AMP, and we said that all of them are in fact formulated with zinc, and when they are formulated with zinc, they show excellent performance against corrosions, and unfortunately they are not that much resistant to high level of color. If high level of color is present in cooling water systems, therefore, when we have, in fact, a high amount of color in cooling water system, and we want to use phosphonate as one of the component of the formula, we ought to select PBTC because it has the highest resistance compared to other components. But when the level of the chlorine in the water is not that much, we can use HDP instead of PBTC. And for HBTP, we said that we at least need 25 to 50 ppm of calcium to create that uh, protective film. And of course, the same happens to HPA. HPA also requires some calcium to create that protective film. So this is the end of our episodes. I hope that you have enjoyed every moment of these episodes, and you will be able to use some of these materials, to use this information provided on these episodes to specify the formulation for your corrosion inhibitor, and select the best type of corrosion inhibitor for your application. Like always, I wish you a good day and enjoy your life.